Hello, everyone. My name is Shreyan, and I work at the Institute of Computational Perception in JKU Linz. And today, I'm going to talk to you about frequency-aware receptive field regularized CNNs for emotion recognition in music. So this is a brief agenda. I'll go over the overview and see what approaches we tried, what worked, what didn't work, and the results and the conclusions we can draw. So the main takeaways that I want to share is that we tried smaller networks and larger networks, and we see that for larger networks, if we restrict the space, the receptive field that the network sees from the input, the performance improves, and we think it's because it avoids overfitting. And also for inputs having spectrograms, we see that the frequency context helps, and I'll share how we do that. And also we used some ensembling approaches which improved our performance a lot. So you can see our that is our main result, which is 0.15 of PRAOC compared to the baseline. So I'll quickly go over the overview. As we know that the task is an instance of auto-tagging, and the current state of the art in many audio tasks, they use CNNs in a VGG-like architecture, which is also our baseline. And we use input as spectrograms, which is the frequency time representation of audio. We also observed that in spite of deeper architectures like ResNets working quite well for vision tasks, they don't generally perform well for audio tasks, and that's one of the things we try to address. We trained VGG-like model, ResNets and CRNNs as baseline models because they don't improve from the given baseline a lot, and we actually see that the ResNet performs slightly worse than the baseline. So the question we ask is deeper actually better for audio tasks? And because the ResNets, they try to address the shortcomings such as vanishing gradients, but that doesn't seem to work quite well here. What we also observed was that Hershey et al. Used ResNets quite well on audio clips, which is a very large data set of 70 million audio clips, and it works quite well there. So one of the things that large networks have different to smaller networks is the receptive field, which is the pixels in the input space that actually affect the output neurons. So with this formula, we can calculate the receptive field that the output sees on the input. And here S are the stride values, and K is the kernel size of the layers. And we can also calculate what is the effective receptive field. So the formula on the previous page gives us the maximum receptive field that is available to every output. But all of the input doesn't need to actually affect the output. So we can use gradient methods to calculate the area in the input space that actually affects the outputs. So we see that ResNet has a much higher receptive field than smaller networks like VGGs. So what we tried to do was we reduce the receptive field in our network by changing some of the filter sizes from 3x3 to 1x1, and we use the filter size as a hyperparameter. And we see that as we decrease the maximum receptive field size, our performance usually improves. Okay, the other thing that we used was frequency-aware networks, which is a very simple concept. So what we do is we take in every layer we take the input and we pad it with a layer with a channel which has values from -1 to 1, and it goes from every frequency value has a value between -1 and 1. So it's like a gradient channel, and we do this in every layer. So that improves our performance also. We also use something called shake regularization, which is basically adding kind of a noise in the training, in the ResNet training. So in the forward pass, we have random alpha, which so we have two copies of the same model, and in the forward pass, we randomly add parts of both by selecting a random alpha. We do the same in the backward pass, and similar in the test time. So that helps in improving the performance. Uh, Finally, we do stochastic weight averaging for our networks, snapshot averaging, and multimodal averaging, and we see that the and ensembling really helps in improving our performance. These are the results. So Shake FA ResNet is the ResNet with frequency awareness and shake regularization. FA ResNet is just frequency aware, and the average ensemble is the ensemble of all our models. So in conclusion, receptive field regularization is useful to avoid overfitting, and frequency aware networks improve performance given the spectrogram is an input, and ensembling helps. In the future, we would also like to consider more of the temporal context, because this we haven't used much of temporal context here, and for emotions, we feel it might be useful. We would also like to use perceptual features, which are so we can use perceptual features as an intermediate prediction to predict the emotions and moods further on. Yeah, thank you.